All right, so hopefully we're pretty comfortable naming any type of wave function using the chemist's terminology. Let's switch to a clicker question and just confirm that that is in fact true. So what's the corresponding orbital if we talk about this state, 5, 1, 0? And you can go ahead and give 10 seconds on that. I'll have to try these new timer functions for you. I didn't realize they were. Okay. All right, 77%. So that's okay. You don't have to memorize things as I speak. You just need to go back and look at this and make sure you understand how to name it and that you'll be able to, for example, by next class, get a similar clicker question correct. And good job to the 77% that did get it. So I think we're safe to move on here. And I just want to point out that now we have these 3 quantum numbers. The reason there are 3 quantum numbers is we're describing an orbital in 3 dimensions, so it makes sense that we would need to describe it in terms of 3 different quantum numbers. And the complete description, as I said, is from N, L, and M. And when you talk about N for an orbital, it's talking about the shell. That shell is kind of what you picture when you think of a classical picture of an atom where you have one energy level, the next one is further out, the next one's further away. That's kind of your shell that we're discussing. L is the subshell here, and then we have M, which is finally the complete description of the orbital. And what you can see is that for any n that has an L equals 0, you can see here how there's only one possibility for an orbital description, and that's why we don't need to include the M when we're talking about an s orbital. The other thing that we know, which is what we were just discussing when we were going through the table, is how this all relates to energy. And I want to really highlight here, we're talking about for a hydrogen atom, orbitals with the same n value have the same energy. Some of you might be saying in your heads, wait a second, I happen to remember from high school that p orbitals have different energies than, for example, s orbitals. And that is not true for one electron atoms. We're going to get to more complicated atoms eventually where we're going to have more than one electron in it. But when we're talking about a single electron atom, we know that the binding energy is equal to the negative of the Rydberg constant over n squared. So it only depends on n. So for example, if we're talking about the n equals 2 state, all of these 4 orbital descriptions are going to have the same energy. And we can generalize to figure out, based on any principal quantum number n, how many energy levels we have that are of the same, or how many orbitals we have of the same energy. And what we can say is that for any shell n, there are n squared degenerate orbitals. And the word degenerate simply means same energy. So you have n squared orbitals that are of equal energy when they're degenerate. So let's look at where this comes from with an energy level diagram here. So what you can see is, again, we've got this ground state. My pointer's kind of coming in and out here, I think mostly out at the moment. So if we go to the ground state, what you see is we're at that lowest energy level, and we only have one possibility for an orbital because when n equals 1, that's all we can do. So that's the 1s orbital. We have n squared, or 1 degenerate orbitals. When we talk about the n equals 2 state, we now have 2 squared, or 4 degenerate same energy orbitals. And those are the 2s orbital. And then we also have the L being equal to 1 orbital. So those are going to be the 2px, the 2pz, and the 2py orbital. All 4 of these orbitals have the same energy. They're degenerate. And as we go up to the next energy level, which is based on n equals 3 principal quantum number, well, now we have, again, the s. So we have the 3s orbital. We're going to have 3 3p orbitals, right? So we'll have 3px, 3pz, and 3py. And now we're actually also going to have 5 different possible L equals 2 orbitals. Does anyone remember the L equals 2? Yes, everyone remembers. Good. So we have 5 possible d orbitals. We'll call these here the 3dxy as the subscript, the 3dyz, the 3dz squared, the 3dxz, and the 3D x squared minus y squared. Let's see if this is working again. And it is. So what do you need to know here? What you need to know is that when m equals 0, it's 3dz squared. That's it. Again, these other p, or the dxy, dyz, those are going to be those more complicated linear combinations. You don't need to worry about them. Eventually, you will at least need to know the labels and know a little bit more about them. And in the second half of this course, Professor Drennan's going to talk to us about transition metals in depth. And that's when we'll really delve into d orbitals. For right now, you can kind of put the d orbitals in the back of your head. You need to know how to think about them in the same way we think about s and p orbitals. But for example, you don't yet need to know what all of the names are except for this 3dz squared here. So we'll wait on that until we start talking more specifically about atoms where the d orbital becomes very significant.